So, welcome back. In the previous video, we set for ourselves the somewhat ambitious goal of going from the left hand column where the vehicle specifications are given, and from that arriving at the right hand column where the motor specifications are given through systematic application of just one equation, F is equal to ma, which is what we are going to do now. Let us look at the forces acting on a vehicle. Again, you will be familiar with most of the things. F is equal to ma, and acceleration, I am just rewriting it as rate of change of velocity, dv by dt, and m here is the gross vehicle weight, v is the velocity of the vehicle, and this F is what is called the acceleration force. Where does the acceleration force come from? The motor delivers what I have written in the last line as Ft, which is the traction force. Now, to the traction force that the motor is delivering, there are many claimants who will take away some of the traction force. There are three claimants to the traction force. Fg is the gradient force, Fr is the rolling resistance friction, and Fd is the air drag. After all of these three claimants have taken away some part of the traction force, what we are left with is F, and that F is what contributes to the acceleration of the vehicle. So far, is everything clear? No problem? So, let us move on. Let us look at each of the terms that we saw in the last line of the equation one by one. So, where does the traction force come from? I told you the traction force comes from the motor, and the traction force is the torque applied by the motor on the wheel divided by the radius of the wheel. So, the motor is actually applying a torque at the hub of the wheel, and I have denoted that as tau w, w being for wheel, tau is the torque, and that divided by the radius of the wheel is the force that the vehicle will encounter. And how much is the torque applied at the wheel in relation to the torque applied at the shaft of the motor? The torque at the shaft of the motor is conveyed through a gear mechanism. Gear is a generic word, it may be a belt and pulley combination, it could be anything, any transmission with a certain ratio is the transmission through which the torque is conveyed, and that gearing ratio I have denoted it by G, and the transmission mechanism has its own friction. So, it will eat up some of the torque, and that efficiency I have denoted by eta. So, the motor torque amplified by the gear ratio multiplied by the efficiency of the gearing is the wheel torque. Is this clear? Please feel free to interrupt me if any step is not clear, because very soon I am going to mix everything up and make a very messy looking curry. The next term in the equation is Fg, the gradient force, which from your high school physics you know is mg sin theta, where g is the acceleration due to gravity and theta is the angle of the gradient. And then there is Fr, the rolling resistance, which is nothing but the frictional resistance at the wheel or the contact between the tire and the road, and that is mu mg cos theta, where mu is the coefficient of friction. This again is an equation that you will be familiar with from your high school physics. I will not go into the details. On air drag I want to spend a little bit longer time. The it is a very curious kind of force. All the other forces that we have seen so far are forces that do not change as the vehicle moves. The funny thing about the air drag is that when you start moving, there is no air drag. As you increase your speed, the drag also increases. So there is a kind of circular relationship. The drag force affects the speed like all other forces. All forces, when they affect the acceleration, they end up affecting the speed. In the same way, the drag force affects the speed, but in turn the drag force is also affected by the speed. So it becomes a circular relationship, and I want you to pay attention to it. The drag force is half rho CD AF V squared. All the terms other than V squared are a constant. Rho is the density of air, CD is the drag coefficient which comes from the shape of the vehicle, and AF is the frontal area of the vehicle. All these things do not change when the vehicle is moving, but as the vehicle starts moving, what does change is the velocity, and when the velocity changes, the force of air drag itself changes. So now that we know all the forces, let us look at all of them together. F, what did I say F is? F is the acceleration force, and this acceleration force is equal to the traction force minus the gradient force minus the rolling resistance minus the air drag. And what I have done is I have simply divided the entire equation by m, the mass of the vehicle, just to simplify its form. So when you see in the last equation, instead of having f which is m into dv by dt, if I divide the entire equation by m, I am just left with a dv by dt term, and then all the other terms also I can divide by m. Here the m will go away, and here an m will come in the denominator, and I have just clubbed all of those terms and denoted them by a and b. For ease of recognition, I have highlighted the terms a and b in red color. So it is just a simplified way of writing the more monstrous equation that you are seeing in the first line. Whatever equation you are seeing here is the same as the equation that you see here, where a and b stand for these two things. Is this clear? If any of you have a difficulty in following this, please ask me. And I want you to appreciate that the first term is the traction force, the next thing is the gradient force and the rolling resistance force, and the last term is the air drag. And the reason for my writing the equation like this is that this now becomes a differential equation in V. There is one term which has dV by dt, another term which has V squared, and another term which is independent of V. If I solve this differential equation, then I will find that V is equal to a terrible looking expression like this. This is not a course in mathematics. Anyway, you all should be knowing integration. You can brush up your knowledge of integration and figure it out for yourself by solving that differential equation. All that I want to point out is that I am using a technique called variables, separation of variables in solving a differential equation. Then the equation becomes of this form, and then I can solve the differential equation in this way. And by applying the boundary condition that I am starting from rest, it means when t is 0, v is 0, I find that the constant of integration becomes 0. The interesting thing is that now if I substitute instead of t infinity, You may think that because there is a traction force coming from the motor, it is speeding up and speeding up, therefore after infinite time it will be going at infinite speed. The longer you wait, the faster it will be going. But actually the answer is somewhat counterintuitive. If I substitute infinity for t, then this denominator becomes infinite. If the denominator becomes infinite, then this term becomes 0. 1 minus 0 becomes 1. So what I am left with is v is equal to root of b by a. So just by looking at the terms b and a, I can predict what is called the steady state speed. It means no longer how long I drive, no matter how long I drive, I will never cross this speed. That is called the steady state speed. We will soon see it graphically. I can plot velocity as a function of time using the equation we just now saw, and for a typical example where I plotted when I applied a 6 Newton meter torque, how the speed increased over time is shown here, and if I calculate root of b by a, I get 37 kilometers per hour, and you can see that if I project this long enough, it seems to asymptotically reach 37 kilometers per hour. It will never cross 37 kilometers per hour. You know the meaning of the word asymptotic. It means it will come closer and closer to it but never touch it. So the asymptotic speed that it will reach is only 37 kilometers per hour. I will never be able to cross it. On the other hand, if I turn the throttle a little bit more and increase the torque from 6 Newton meter to 10 Newton meter, then the steady state speed becomes 58 kilometers per hour. But no matter how much I increase the torque, always the final speed is bounded. It is not as if the speed is going to go on increasing forever and it will become infinite. No, it will always reach a certain threshold. And why does it happen so? Because of air drag. As the speed increases, air drag continuously increases and limits the speed and clamps it to a certain value. This is the interesting thing about air drag. Now, in an actual driving scenario, what I will be doing is, I will normally start, let us say the signal is red, I am waiting, and then the signal turns green. I want to be first off the mark, I give a high throttle and start. And very quickly I will reach a certain speed. After that I will down the throttle and just maintain the speed, or I will want to accelerate less fast. For those kind of scenarios, can we still use the same equation? Because our equation, whatever we developed, has one limitation. It always assumes that in the beginning speed is 0 and after that the torque is constant. But for these kind of drive cycles where torque is changing midway, and when the torque is changing the speed is already high, how can we use the same equation? It is very simple. We can just cut and splice and assemble like a jigsaw puzzle. Let us say for the first 40 seconds I am giving 10 Newton meter torque when I am starting from rest. The signal turned green, I am giving 10 Newton meter torque and accelerating for 40 seconds. I have reached a speed of 20 kilometers per hour, and after that I am lowering my throttle to 6 Newton meter. Then subsequently I will be travelling in this graph. So I have travelled initially like this and then I am travelling like this. So by assembling the two together, I can construct my overall velocity versus time graph for the case where the torque is changing midway through the ride. So far is it clear? No problem? So now that I can plot the velocity versus time, I am getting a little greedier. Can I also plot the distance versus time? You already saw a complicated equation giving velocity as a function of time. It was marked as equation number 4. We will pull back that equation which expresses velocity v equal to on the left hand side, and on the right hand side there is a complicated expression which has a t in it. How do I find the distance? Knowing the velocity as a function of time, how do I find the distance? Again integrate. It looks quite hideous. I won't go into all the details. You can figure it out at leisure. If you have forgotten your integration, you can brush up. But the only clue I want to give you is that this equation is of the form this, and if you apply this rule, you can derive this. Only thing you have to remember is that after you integrate, there is a constant of integration which is minus 1 by a log 2, and if you apply that, then the equation for distance becomes this. Now, if I were to plot this as a function of time and see how the distance changes, then if I travel at 6 Newton meter torque, this is the way distance will change. You can see that after about 170 seconds I have covered a little more than 1 kilometer. Whereas if I apply 10 Newton meter torque, after the same 170 seconds I have covered more than 2 kilometers. So this is how the distance changes with time. So now that we know so much about the way the vehicle responds to torque from the motor, for different modes of driving that we saw at the beginning, we can plot the respective torque and speed combinations based on the vehicle performance. So the x axis here is what is called the k RPM, or in thousands of RPM of the motor, and the y axis is the motor shaft torque, and at different operating points I am plotting the torque versus speed combinations based on the vehicle specifications and the equations that we just now derived. And as I told you, some modes of operation will happen for hours together, some modes of operation just happen for a few seconds. You can see 8.5 seconds and things like that, 13 seconds for overtaking, and based on this I can plot different points. By joining these points, I can generate the torque speed curve of the motor. I can do the same thing with the power versus speed. What I want you to see is, normally when people say what is the rating of the motor, they will say 1 kilowatt, 10 kilowatt, 5 kilowatt, or 3 HP, 8 HP. This is okay for the motors that you are using to pump water in your house, but in an electric vehicle you can see that in different operating modes the power can be very, very different, and it is not only the power that matters but the speed at which you get the power. So unless you describe the combination of power versus speed or torque versus speed, you are not really describing the motor properly. Just by saying, oh, here this is a 3.5 kilowatt motor, tells you nothing about the motor. Fine. So based on all of this analysis, I will show you how the torque speed curve and the power speed curve for continuous operation can be generated and depicted. What you are seeing is for the continuous operating modes, and the blue curve is the torque versus speed curve, and the orange colored curve is the power versus speed curve. And I can do the same thing. This you can see that the power is never crossing 10 kilowatt and the torque is limited to less than 50 Newton meter, and this operation with 49 Newton meter as is given here can happen for hours together. But for short term operation where I need a lot more torque, I can draw a separate set of graphs where the torque can be as high as 65 Newton meter and the power goes up to 15 kilowatts. So, without looking at the physical structure, size, shape or anything about the motor, without knowing anything about what kind of a motor it is it an AC motor, is it a DC motor, is it an induction motor, without knowing anything about the motor, I have derived the specifications of the motor, I have even drawn the curves, performance curves of the motor. And another interesting thing I want you to look at is that when you use the equations we developed and for different operating speeds within any one drive mode, if you look at the different operating speeds, different speeds through time, we already saw that the velocity changes based on the time. At different points, if I were to see what is the power and what is its speed in kilometers per hour, I will be able to estimate the energy efficiency as they call it, which is watt hours per kilometer. You have already gone over it in the earlier lectures and you understand what it is. I will not dwell for too long. All that I will say is that I want you to look at this slightly interesting way of rewriting it. Watt hours per kilometer can also be written as watts per kilometers per hour. Kilometers per hour is the speed, watts is the power. So, the energy required to cover 1 kilometer is the same as the power required per kilometer per hour speed. So, this is what I am using here. Watt hour per kilometer is the same as power divided by velocity, where the velocity is expressed in kilometers per hour. But since I want to convert this to meters per second, I just have to multiply it by 3.6. And I know that the power is torque into angular speed. The subscript m stands for motor. The motor torque multiplied by the angular speed of the motor is the power, tau omega, and the angular speed of the motor is gear ratio multiplied by angular speed of the wheel, and the angular speed of the wheel is V by R, where this V is in meters per second. So, if I use this equation and substitute it here, I will find that watt hour per kilometer is equal to motor torque into gear ratio divided by 3.6 into R. What is nice about this equation is it tells us clearly what is happening. The term 3.6 is a constant, it is just a number. The R and G are again constants because they just depend upon the vehicle. The vehicle has a certain radius and a certain gear ratio. The only thing that depends upon how I drive the vehicle is the torque, and the watt hour per kilometer or how much the battery is getting drained per kilometer simply depends upon the torque. If I give a high throttle, it will get drained more per kilometer. If I give a lower throttle, it will get drained less per kilometer. And this intuition is not very obvious if you do not look at this equation, because I will think that if I give a high torque, I will cover 1 kilometer in less time. So, battery is getting drained at a faster rate because of my high torque, but I am also taking the higher rate of discharge for a shorter time. On the whole, is the battery getting drained less or more? Is not very obvious, because there are two factors at play which are offsetting each other. But this equation clearly tells us that if I apply a higher torque, my battery will get drained more. The watt hours of the battery will reduce more, and we can see that again by plotting the watt hour per kilometer with respect to the torque in different drive modes. The interesting thing that I want you to see is that the different drive modes call for different torques, and the greater the torque, the greater is the watt hour per kilometer. And the most interesting thing about this graph is that all the dots are on one straight line which passes through the origin. Can you tell me why? Why are all these dots on one straight line passing through the origin? Yeah, the answer comes from this. If I put torque is 0, then watt hour per kilometer is 0, and after that it is just a straight line, linear proportion. Feel free to ask me.